Anytime.
All right.
Yep.
All right. Well, good afternoon, everybody. Thank you for coming. I will introduce myself. I'm Ángel F. Corraliza. Most of you know me. I'm faculty here, right? Teach some of the classes some of you have taken with me. And I will be giving today's colloquium together with Qiao-Jun Lin, who is a postdoc in my research group. Qiao-Jun has been here for almost 2 years now. You've been? No. More longer than that, right? 1.5, almost, yeah, 1.5 years. She first did senior PhD thesis from the last parts of the PhD with the group, and then she's now been working as a postdoc. So today we're doing something a little different, but if you follow that previous talk that I gave back then with Victor, you know that this is not the first time we did that. And that's that we're going to split the talk in half. So the first half of the talk is going to be me talking about some of the kind of newer stuff that the group has been working on, and then Qiao-Jun will work on more of the stuff that she's been leading on. And what we're going to do is that we're going to be going up in spatial scale, from like smaller scale to like larger scales, and we're kind of going to be putting like all those building blocks together. So that's going to be the topic of today's colloquium. So it's going to be more of a lecture rather than like actually going through like a thorough investigation or something. So let's think about this as like an opportunity to like kind of just think about tropical dynamics across different scales and how these different scales are interrelated to one another. So let's get started. So you've all seen this animation before. It's a lovely animation that you can use to kind of think about both the mid-latitudes and the tropics as an integrated system, but also as separate components of our planet. And what's nice about this animation is that you can actually look at the upper and lower parts, which are like the northern and southern mid-latitudes, to see all these storms, right? These are the weather systems that do affect our day-to-day living, right? And you've got all these cold fronts and these warm fronts, and you get these ups and downs in temperature that you see especially during winter time. However, when you look at the tropics, you see a much different picture, right? You see a lot of like deep convection, all these like really deep thunderstorms that you see here over the maritime continent, as well as these like mostly cloud-free or like mostly shallow cloud regions out in the subtropical dry bands. So just by looking at this animation, you can probably correctly guess that the dynamics and thermodynamics that govern the two latitude bands are actually quite different from each other. And you would be correct. So let's look at a quick comparison here. So I like to make these comparisons, especially for those of you that are taking GFT or are taking synoptic meteorology, but don't have necessarily the background in tropical meteorology. So here's a picture of a convective system in the tropics. Here's a mid-latitude weather system, and here's like a rough introduction to both latitude bands. So it turns out that roughly half of the global population is in the tropics, and then the other half is in the mid-latitudes. So the global population is almost evenly split amongst the two latitudinal regional regions. In the tropics, the Coriolis force is weak, while in the mid-latitudes, the Coriolis force is strong. If you were here for Rosa's defense, she actually gave a nice introduction to that. By the way, part of the reason why I'm giving a talk today was that this may have been Rosa's defense date, but now we pushed it back a week, and now I got to give a talk today, just FYI. Random story that doesn't have to do anything with this, but here we go. The big thing about the Coriolis force being weak here and strong here is that it leads to a major consequence, and that is that in the mid-latitudes, temperature gradients are strong. And if you're somewhere up in the troposphere, you will see very sharp changes in temperature, right? And you will feel them at the surface as well. In the tropics, the opposite is what happens. So temperature gradients are fairly weak. And if you're somewhere in the free troposphere, a couple of kilometers from the surface, you would not experience big changes in temperatures throughout the year. They would actually be pretty small. Now, here is where there's an interesting difference here, and that's that if you're a synoptic meteorologist, looking at the mid-latitudes, especially winter, you're really interested in looking at the large-scale behavior, from like going from shortwave troughs all the way to the large-scale troughs and ridges, and the variclinicity, and all these aspects of potential vorticity that we're interested in. So if you're learning about the mid-latitudes, especially in a course, you're actually going to be largely focusing on large-scale dynamics, so things that are on the order of hundreds of kilometers or bigger. In the tropics, however, the topics are slightly different, and here we have coupling about multiple scales. And the things that happen between the individual clouds and the larger scale behavior of hundreds and thousands of kilometers across are actually interacting and communicating with each other in such a way that you actually can't disregard either of them. So This coupling is what makes the tropics particularly unique, complicated, and has been an active area of research. So we are interested in how these cloud systems, this is a picture I took when I was in Puerto Rico a couple of years ago, and these are a bunch of easterly waves that are leaving Africa. One of them was developing into a tropical cyclone. So you see here these two arrows that they mean that this is influencing this, but this can also be influencing this. So what we're going to be talking about today is how this happens from a fairly basic framework, but also emphasizing on current research on these topics. So what I'm going to do today, and this is actually going to provocatively do this, is that we do have a working framework that helps us understand tropical motions, and that is based on the weak temperature gradient approximation. And what we're going to do is that we're going to use this notion of this basic framework to understand a few things. One of them is the mesoscale cloud clusters, the other one be quasi-equilibrium, and then the last one is the large-scale circulation. Qiao-Jun is going to take care of the large-scale circulation here, and I'll talk a little bit about 1 and 2 over here. So first let's talk about the mesoscale convective systems and the cloud systems. And this is going to be based on interaction between gravity waves, weak temperature gradients, and deep convection. Now I will say that I unfortunately got the reviews this morning and the manuscript got rejected, but I will push back and say that the science is still good, and I actually disagree with the reviewers. So, so we'll work on this. I mean, there's some good feedback there on the plots and stuff, but overall I have some major disagreements with that. But we'll keep it at that. So what we're going to talk about is what happens at the smaller scale and why that is important to understand what happens at the larger scale. So here is a cloud system. This is an area of deep convection. You have this big cirrus stack over here, shield, and there's a bunch of little bubbling elements inside of it. What we've observed about these big systems is that they tend to have only 2 modes of vertical velocity in them. So one of them is often called the convective mode, which is a single profile of vertical velocity and heating that covers the entire troposphere. So here's the heating rate. The value doesn't really matter. What matters is that it's just a single polarity through the entire depth of the troposphere from 0 to 14, 15 kilometers of elevation. And then the second mode is the stratiform, which is like a sine wave essentially, which is 0, has a minimum value in the lower troposphere and then a maximum value in the upper troposphere. And interestingly, these two explain the majority of the vertical velocity variance in the tropics. This one explains 2/3, and then this one the other third, or 25% of the variance. Another interesting feature is that buoyancy, so if you've been taking my class 630, or if you've taken 330, you're probably familiar with buoyancy at this point. So we know that buoyancy is associated with acceleration. In the tropics, what we see is, so buoyancy here, this is the buoyancy of a plume, which I'm going to define later on, is related to actual rainfall. And it turns out that when you have a negative value of buoyancy, all the way to very close to 0, you get pretty much 0 rainfall. And once you hit a critical value, which is essentially 0 for all medicine purposes, it shoots up and it goes up linearly, but very steeply. Okay, so it starts raining really heavily, very quickly once you achieve this threshold. But there hasn't been a satisfactory explanation as to why this curve is aligned and why it goes up so steeply. So the idea that I'm proposing here is that in order to answer that question, and the question about the vertical velocity being mostly 2 modes, is that in order to answer that, we need to think about cloud systems or any region of organization that's roughly 100 kilometers across as not a parcel, not a collection of thermals, but as a coupled system, specifically a coupling between the clouds and gravity waves that are responding to the clouds that are forming in this system. So what is this? What am I talking about here? So look at the animation here on the right. So this is a circular region of diabatic heating. So you can imagine that being a cloud. And the color here is a warm anomaly. So the deeper the red, the warmer the anomaly is. So this is a heating that's turned on at time 0, and as soon as you turn it on, you see a ripple going out away from the center, warming up the entire region. Now this looks white, but it's actually like a tinge, it's a tinged yellow, just not very entirely visible on the screen here. So what you see is that at time 0, you develop this ripple that just explodes and goes out in all directions, warming the entire column. So it's not just the cloud that warms, it's actually the cloud and the entire surrounding environment that all warms up in response to the circular region of heating. And you can think about the same thing going on in this region over here. So anytime that you have something like condensation and a bunch of other things that lead to heating here, including radiation, you're going to have a response in the form of gravity waves. So these ripples are known as gravity waves, and these gravity waves are not just going to be warming the region, they're going to be warming the entire surrounding environment. This goes back all the way to the late 80s by this paper by Breifenton and Smollers-Hewitt, where they were talking about this process known as buoyant equalization, which means that the buoyancy of the cloud and the environment roughly equalize with each other. So we're going to take that a step further, and we're going to say that actually this system is going to be a gravity wave that's being damped by the active turbulence in this convective element, as you see here in the schematic. So you can imagine this cloud, there's a bunch of updrafts, there's downdrafts in the downward arrows, and there's this turbulence here in the form of these little rolls in here. And this turbulence here is going to actively try to damp the gravity wave that's responding to the convection as it blows away from this region of convection. So then you have a two-way balance in the momentum equation between the pressure gradient force, which is actually actively being created by the gravity waves. So the gravity waves are trying to accelerate the air into the center of this cluster of clouds here, and then you're going to have a diffusion or like a dissipation that's coming in from the convection in here that's going to actively try to dissipate that momentum that's trying to be created by the pressure gradient force. So you got larger scale pressure gradients bringing air in, and then the smaller scale elements trying to dissipate that out. If you take that and just mix in all these equations together and use hydrostatic balance, assuming that that works at this scale, which it does, then you get a relationship between the first two modes of vertical velocity. So let's do a quick exercise here. So let's assume that this m, this is the vertical wave number, and assume that this is equal to a value of 1. And this is the second mode in the wave number, and that has a value of 2. If we combine the relationship between vertical velocity between the first mode to the buoyancy of the first mode and the second mode, you get this that you see here on the screen. So this W2 is this here, this stratiform profile, and this W1 is just this deep convective profile. And you get that they're related to the buoyancy that corresponds to the stratiform mode here, and then the buoyancy of the first mode here. And then you see that you get M1 divided by M2. And this is 1, and this is 2. And they're exponentiated to the 4th. So you get 1 over 16, sorry, when you see this here, and I subtly messed this up, but it's like roughly like a 16 here when you look at that. So you get that in this system that has this type of balance where the diffusion and the pressure gradient are counteracting one another and balancing each other out, you get that the vertical velocity associated with this first mode has to be about 16 times stronger than the one of the second mode. So this one has to predominate. This one has to be by far the stronger one because of this balance here. So this explains why in the tropics this is the most often observed vertical velocity at the scale of these cloud systems. If that was too mathematical for you, I'll give you a little schematic here to look at this on the screen. So this is actually the buoyancy anomaly of this cloud system, and we've non-dimensionalized the radius because it doesn't really matter. This is 1 to minus 1 is just the extent of the system. So this is like halfway out to the center, and this is like a ring-shaped system, so it's the former of a circle. So here, what you see is that you have a cold anomaly in the bottom and a warm anomaly at the top, and you see that the vertical velocity is coming in laterally and it's going up deeply in these profiles. And the reason why you get air ascending throughout the entire column is that I purposely made this be a combination of a sine, a half sine, and then a full sine here. So this double profile is actually a combination of the two. But the second one, the one that's giving you this shape, is the stronger one. But because vertical velocity so strongly responds to that first mode of heating, you end up getting a deep mode of vertical velocity. So what ends up happening is that you can actually have ascent even in regions where the buoyancy is actually negative because the gravity waves are actually accelerating air in and up these regions regardless of what the buoyancy of the cluster is in the low levels. So you're always going to get that kind of a sense because essentially the waves are actually always going to be creating this motion to be upward. So this actually creates an interesting scenario, and that is that what you really need is that this velocity, the take-home message here is that this deep form of vertical velocity is very predominant and can occur for a variety of different temperature profiles or temperature anomaly profiles. So this makes things like the entraining plume framework that I'm going to bring in now widely applicable for a variety of scenarios. And this is work by Ahmed and Neelan and Skiro and others. And the schematic here essentially tells you that these cloud clusters have a deep inflow profile. And when I mean deep inflow, I mean something like what you see here in the previous image. And that is that you have air coming into the cloud cluster from the surface all the way up to almost halfway up to the troposphere. So let's think about 3 to 5 kilometers up in elevation. And what we're saying here, what I'm trying to argue to you here today, is that this profile of deep inflow is actually a response in the form of gravity waves that are actually accelerating the air into the cloud system in the form of this deep profile where the air is coming in through a deep layer. And that makes the training plume framework very applicable for a variety of convective systems in the tropics. Now, what makes the plume framework interesting is that it allows you to decompose the buoyancy of the cloud cluster into an undilute and a dilution component. So these two, so the undilute component is essentially what you would get from a parcel. So a parcel buoyancy, and then dilution is whatever gets reduced by this inflow that's coming in the form of gravity waves. So the gravity waves are going to be bringing in dry air laterally and drying it up. So if you do that, I'm going to show this plot initially, is that when you combine this with the weak temperature gradient approximation, assuming that the temperatures of the tropics need to be fairly homogeneous, then you get that the temperature of the convective system is only a little bit warmer than the surrounding environment. And when a little bit warmer, I mean like 1/10 of a degree warmer than the environment. And you get a relationship like you see here between rainfall and the column average temperature of that convective system. So rainfall here is shown on the left, so LV, this latent heat of vaporization, P is the rainfall, Cp is the specific heat, and these angle brackets mean averaging or integration over the column. So if you have a temperature anomaly, so this is created by the buoyancy of the system, then after you reach a temperature anomaly of above 0, so you're warmer than the surrounding environment, rainfall shoots up. And it shoots up very rapidly. As you see here, it goes up from an anomaly of 0 to like 0.2 degrees. By the time that you're at like 0.2 or 0.25 degrees, you're raining like 100 millimeters per day, which is like 10 centimeters per day, which is like roughly like 4 inches per day, if I'm not mistaken, if I'm doing the conversion right in my day. So this is really heavy rainfall for like a temperature anomaly that's really, really minute. The corresponding Cape anomalies of the cloud system are shown on the top. So this corresponds to a Cape anomaly of roughly like 100 to 200 joules per kilogram. And if you've done mesoscale meteorology, you know that this is actually pretty small, and that mid-latitude storms actually have Cape values in the order of 1,000. So let's think about it that way. So we usually think of Cape in terms of undilute parcels. So parcels go up, and once they hit the level of free convection, they're just shooting up and going up until they hit the level of neutral buoyancy. But we know, and this is especially true for tropical systems, and this is the work that has been done at this department, especially by Larissa's group, that this actually is not how convective systems in the tropics work at all. And that convective systems in the tropics experience a lot of dilution. So this diagram here is showing you essentially a dilution and undilute Cape component. And the take-home point here is that here is the 0 Cape point here. And the x-axis is the undilute Cape, so this is the parcel Cape, and then the dilution from mixing is here on the right axis. And you will see here that on the left, when you are negative, you have no rainfall. Rainfall just increases very dramatically on this right upper part of the diagram. But if you look at the rainfall rates, we know that realistic rainfall rates are actually at this like lower yellow colors here. So you're only getting realistic values over here, which is telling you that you rarely get these really deep excursions you can see to the right. You're almost always close to this dashed line. So in the tropics, actually, Cape effectively is very close to 0 because the dilution and the undilute component are actually mostly canceling each other out, and what you're left is with a residual that's on the order of like 100 joules per kilogram. Notice here that these are on the order of several thousand. So you're getting 1,000 minus 900, and you get like 100. So you get these two canceling out to a very, very large degree, leaving you with a temperature anomaly that's actually quite small that needs to be consistent with the weak temperature gradient approximation. And this is also consistent with the zero buoyancy approximation of staying in the environment and other studies that have come out thereafter. This is also consistent with the observations. So I showed you earlier that this line goes up steeply and linearly after you hit a threshold temperature. And this is what you see in the reanalysis, that you don't really have rainfall. So your buoyancy is essentially giving you no rainfall, and then you hit this threshold, and then all of a sudden rainfall shoots up steeply. So the theoretical curve is this light green line here, and then the observed rainfall rates binned are actually these dotted lines. So this is like a histogram, to the histogram in shaded, and then the points that I want to pay attention to are these circles, which are like the mean point of each bin here. So you see that the rainfall does reach some kind of critical point, and after that it really just shoots up. There is a discrepancy here between the theory and observations for a variety of reasons that I'm not going to discuss. But overall, once you get the steep rainfall right here, the line is actually mostly linear and is following the theory reasonably well. Okay, so I'm going to move on to the next topic, but while I do that, I'm going to recap what this all means, right? So you have this coupling between the gravity waves. So you have a convection here, and you have gravity waves, and they're expanding laterally very, very quickly and homogenizing the temperatures. And you're only left with a small temperature anomaly in the middle through these dissipation processes in here. So, and what I said previously is that this actually causes rainfall to become a linear steep function of the buoyancy. But you don't have to go far away from zero buoyancy to get a lot of rain. It only is a small excursion. And it turns out that in regions where convection is very common, buoyancy is actually really, really close to zero. So last time I actually didn't talk about this line here at all for a reason, and that's because I want to talk about it now. So this here corresponds to this diagram here. So this is a histogram of buoyancy in the tropics, and you'll see that the scale is actually logarithmic. So this here is actually quite a big difference between this here and this here. But what we see is that in the regions where convection is very common, buoyancy is very, very close to zero. So you've got buoyant neutrality in the regions where convection is very active, and these really heavy rainfall events are only small excursions away from this zero buoyancy. So you have essentially neutrality. So this is actually related, and it's actually, you can define this as convective quasi-equilibrium. This is actually a specific form of it known as in training convective quasi-equilibrium because it takes into account the effects of convection. So essentially this action of the waves and the convections are always keeping buoyancy very, very close to zero. So here are the definitions. So in these regions where the convection is very active, you have this cloud system over here, and the environmental temperature and the environmental the cloud temperatures of this TC and T environment are almost equal to each other. They're almost equal to each other. So that means that the buoyancy in this region is really close to zero, which means that K is almost zero. Not exactly zero, but almost zero. And you see here this under the epsilon here, so that to imply that this is the entraining cape, right? So you can still have parcel-based cape that's large, but the entraining cape is very close to zero. So now let's consider a region like those of active convection. So you have a cloud system like this, so here's a bunch of clouds, and then these clouds are actually forcing gravity waves like the animation that we saw in the previous animation. Those gravity waves are going to expand in all directions, and they're going to adiabatically compress the column in such a way that after a certain amount of time, the temperature of the clouds and that of the environment are going to be adjusted to be more or less the same. So now imagine that you have a cloud in an environment like this. So these are the clouds here, these circles are the clouds, and this is the environment. So the gravity waves, these cloud systems are a really small fraction of the total location, but through the action of gravity waves, they can actually warm up the entire region here and bring it to be the same temperature. And it turns out that this actually occurs more commonly in the lower troposphere because actually most clouds that you see in the tropics are actually pretty shallow clouds. And if you do all the math and work it around, you find that the time scale in which the environmental temperature equals the temperature of the clouds is only dependent on two things. One of them is the speed of gravity waves. So some gravity waves, the deeper clouds have faster gravity waves, shallower clouds have slower gravity waves, but also the separation between clouds. And it turns out that because shallow clouds are so common, especially the congestus and the shallow clouds, that the separation between those clouds is really small. And that actually wins out. So that causes the temperature between the clouds and the environment to be very, very close to each other in the lower troposphere specifically. It can happen higher up, but it's much slower and it takes much longer. And this is work that has been done by multiple authors, especially Huang, who has shown that this, known as lower tropospheric quasi-equilibrium, means that these two are actually similar to each other, specifically in the lower troposphere. However, we've assumed that the temperature, previous studies have assumed that it is actually a temperature using kind of mostly like undilute, saying that in the lower troposphere the effects of dilution are pretty small because you don't have enough time for the effects of dilution to take effect. But if you do an analysis, a scale analysis, you find that that's actually not the case. The effects of dilution are actually really important, even in the lower troposphere. So what we're going to do, what we did here to show is that we're going to bring, again, this entraining plume framework and assume deep inflow, and say that the saturation moist static energy, so this is the moist static energy that a saturated column would have, is actually proportional to the environmental temperature. And that the saturation moist static energy of the environment, which is approximately equal to that of the clouds because we're assuming that they're going to be adjusted to be the same, is given by the boundary layer moist static energy and the lower troposphere moist static energy. And these W's are actually wave functions. So you're at, there's a fraction, so this is less than 1, this is less than 1, and they add to 1. So depending on how the profile of inflow is, your plume can have more boundary layer MSC or more lower troposphere MSC. And we can examine all sorts of fun scenarios with this, but I'm going to specifically focus on one. And that is if your boundary layer is really, really thin, so it's really, really shallow, and your lower tropospheric layer is deep enough, so that layer of entrainment is deep enough, then it turns out that your saturation moist static energy is actually going to be approximately given by the moist static energy of the lower troposphere, plus some constant that I disregarded here for the sake of simplicity. So what ends up happening here is that if your entrainment is really, really strong, it turns out that these two are going to be co-evolving at the same rate following the horizontal flow. So then you find that the lower tropospheric environmental temperature and the lower tropospheric cloud temperature follow the horizontal flow and they co-evolve at the same rate. But because this is mostly equal to this, if you do some math, and I can show you the math if you're interested, it turns out that these two simplify to this equation here on the right. And this is the saturation specific humidity minus the humidity, which is often known as the saturation deficit. And this is the horizontal Lagrangian derivative. And what I am going to tell you here is that this really, really strong entrainment limit implies that this difference of the saturation deficit is actually conserved following the horizontal flow like a potential vorticity is. So this is really interesting because if you look at this animation and you take the limit of the weak temperature gradient approximation, which means that the saturation deficit stays more or less constant throughout the tropics, then it follows that what's actually really evolving is the specific humidity. So the humidity is the one that's actually quasi being conserved following the horizontal flow. And I'm going to start this animation so you can see that actually it almost does look like the specific humidity is quasi-conserved following the horizontal flow. Because if you look at this, you can imagine that there's like trade winds moving in it, and you can kind of almost see that the humidity is just being affected. And you're not seeing like big increases or decreases in humidity throughout the tropics, which is really, really strange. But the math tells you that this is what is going on. So why is this what's going on? We know that humidity can come from a variety of sources. It can be from condensation, from evaporation, surface fluxes. There's a ton of sources of states and humidity. So why is humidity quasi-conserved under this particular form of quasi-equilibrium? So remember this diagram here that I just showed you that tells you that the environmental temperature and the convection temperature have to be more or less the same. So that means that all the processes that can potentially change the temperature of the clouds, they have to be canceling out. Specifically, in this framework, the processes that would change the temperature of the clouds are actually those that change this moist static energy. So all the processes that change the moist static energy in the vertical specifically, they also must cancel out. Which means that the vertical advection of moist static energy, the radiative hitting, and the surface fluxes have to cancel each other out, especially in the limit where the free troposphere is big enough. So they have to cancel each other out in order to maintain this neutrality of quasi-equilibrium. And this is really weird, But essentially, if you ever change the MSC here, so if your moist static energy here changes, the temperature of the cloud changes. And that means that this temperature has to change as well, because the gravity waves are exploding in all directions and compressing the column. So for these two to be the same, these have to cancel out. And actually, this is consistent with observational studies. So this is a paper from Inoue et al. 21, maybe 22. I got the date wrong. But what this group of people saw, by the way, Kuni Inoue is a former student from this department. So what they've been working on, and this has been work that they've been working on for years on end, especially with, all the way up when he was a student with Larissa, is that when you look at probability of amplification, so the red colors mean that the probability of rainfall increasing is high, and blue means that the probability of rainfall decreasing is high. What they found is that this probability of rainfall increasing or decreasing is largely related to the advection of moisture. And the other processes actually do not explain as much variability in precipitation as that advection of moisture does. So that actually does imply indirectly that all the other processes have to be canceling out, and that is this moisture transport that's happening in the tropics that's really determining whether it rains or it does not rain. But here's the last consequence, and with that I'll pass the baton to Qiao-Jun. If you take this to its ultimate limit, that you can only move moisture horizontally, and there is a quasi-conserved tracer. If you average out along time scales, that means that you cannot change your moisture locally, right? That's fixed climatologically. But you can still have advection. And that advection has to be canceling out because climatologically you're not changing the moisture in your particular location so long as your climate is stable. So that means that your horizontal advection has to cancel out in that location. So how do you do that at long time scales? The only way that you can do that is that the mean circulation has a specific form of advection that's actually being opposed by eddies. That's the only way that you can do it. So the horizontal circulation, in this case the Hadley cell, that's advecting moisture towards the equator. So you have a moisture gradient like this, and the winds are coming this way. So you're getting drying from the Hadley cell, bringing air inward. And to maintain constancy over time, you need an outward force in the form of eddies. And that's actually the work that we talked about like a year or two ago. That means that you have to, if this is a negative and a force that's deepening the gradient and bringing dry air from the subtropics in, you need to have a high frequency component that's actually pushing against and bringing moist air out. That's the only way you can have it, because all the other processes in the column are canceling each other out in order to maintain quasi-equilibrium. And that leads to the final part of the study, which is what Qiao-Jun's been doing, which is the interactions between the Hadley cell and these. We're going to talk about many ways, but specifically TD type waves. So without any further ado, Qiao-Jun, you have the mic. I know they don't need me with a mic because I'm loud enough, but but yes, mic.
So hi everyone, can you hear me? No.
Yeah, put the microphone on.
I heard that.
Can you hear me? Okay, I will make a short presentation about my current work. There are three keywords: Hadley cell, instability, and tropical depression type waves. First, you have to know what TD type waves, and there are regions of anomalous high and low pressure that are connected with the convection. And the T type waves usually induce a stronger low-level rotation. They are more active in the summer. They serve as a seeds for tropical cyclone development. Not only in the Western Pacific region, you also can observe the T-type waves in the Atlantic Ocean and the Eastern Pacific region. The shading shows you the wave barriers. And the contour is a column water vapor, background column water vapor. You can find that the wave, they usually occur in a region with stronger horizontal gradient of column water vapor. And they will induce the rotation, transport the dry air to a tropical, transport the moist air to extratropical regions. They will induce a polar aiding motor transport. So they also play an important role in the hydrological cycle. Despite decades of research, there's no agreed upon theory that describes their existence, structure, and growth. In the recent studies, Myla and Corraliza found that in the observation, all oceanic T-types are motion mode. Why is it motion mode? There are three basic characteristics of a motion mode. First one, the system must be in a weak temperature gradient balance. And Ángel had mentioned that. So this means the vertical elevation of dry static energy should be balanced by the apparent heating. Second, the moisture static energy of a system should be governed by the moisture fluctuation. This means dry static energy is relatively small, and the wave moisture exhibit a large moisture fluctuation that is highly correlated with the precipitation anomaly. The authors also found that the growth of the moisture anomalies in all oceanic T-type waves is largely determined by the elevation of background moisture by anomalous marine winds. This process was referred to as the moisture vortex instability. So now we know that the growth of the moisture mode, for example, the T-type waves, is largely determined by the MVI, moisture vortex instability. Adams, Corraliza, and Maida, they also proposed that in a two-layer models, this meridian moisture gradient is unstable to moisture mode, and that can be associated with the Hadley Cell. And I has mentioned that the Hadley Cell can transport the moisture to the tropical, converted here, it means dry in the extratropical region. There are the large meridian gradient of moisture. And then the moisture mode wave can go from MVI, extra the energy from the background. So then they will induce the 18 moisture fluxes. And then they play the role in the rotation. So they will transport the moisture to the extratropical region, affecting the gradients. So we think that if the moisture T-type waves are the result of the instability associated with the Hadley Cell, we should observe a clear relation between the two in real analysis data. We also want to answer the questions: what determines the wave variability? Why is the wave variability stronger in the northern hemisphere compared to the southern hemisphere according to the previous studies? How is the wave variability linked to the Hadley Cell? In these studies, we use RFI reanalysis data. We also apply the filtering in space and time to return the T-type wave signals. So first, we need to make sure each processes have a good correlation coefficient. We want to make sure this process is correct. So first, we need to see a clear relation between wave variance and AD moisture fluxes. We consider the variance of T-type wave filter column moisture, and I will call it as a moisture variance later. We should see a clear relation between the two. So showing in the contour is a moisture variance, vector is AD moisture fluxes, shading is a fluxes intensity. For the boreal summer and austral summer, as I say, T-type waves is more active in summer. So you can see that the boreal summer, there are stronger signals in the Pacific region and the Atlantic Ocean. And there are stronger AD moisture fluxes, especially polar AD moisture fluxes. In the southern hemisphere, during the austral summer, the signal becomes stronger, especially over Warm region.
Wait, can you just repeat what the contours versus the colors are?
The contour is
activity?
the moisture variance.
The contour is the moisture variance.
Yeah, previous studies usually consider brightness temperature, but now we want to connect their relation with the moisture, so we consider moisture variance.
Okay.
So when we consider the monthly value, variables average over 10 to 30 latitudes. Northern hemisphere, southern hemisphere, x-axis is moisture variance, x-axis is AD moisture fluxes. We can see a good correlation coefficient for them, and especially northern hemisphere has a stronger wave signals, consistent with the previous studies. Second one, we should see a clear relation between the instability and the wave variance. Why is the instability? A moisture mode level from the MVI have a growth rate defined by these equations. That's related to the first one in Tau C, convective moisture adjustment time scale, a sensitivity of precipitation to column moisture. The K are related to the wave number. The beta Q is measure of the strength of meridional moisture gradient, and also related to the planetary vorticity and the gross stress stability. When we consider the beta Q divided by Tau C, we can get this ratio related to the meridional precipitation gradient. Okay, consider this relation into this part. And we define this ratio as the FQ, and I will call it as instability. Because based on this definition, we can rewrite growth rate like this format. So the growth rate of the moisture mode is determined by the wave number and the FQ. and wave number of specific waves is constant. So the growth rate should be determined by the instability, the FQ, and we should see a clear relation between the wave variance and the instability. So the shading show you the instability related to the marginal precipitation gradients. Y-axis is latitude, x-axis December to November. The contour is moisture variance associated with the TD-type waves. There the results show you multi-year monthly zonal mean result. So you can see the moisture variance is especially correlated with the instability. And the same when we consider the average over 10 to 13 latitudes, northern hemisphere, southern hemisphere, x-axis instability. We can see a clear relationship. Stronger instability, stronger moisture variance. Especially northern hemisphere has a stronger instability compared to the southern hemisphere. So the question is how to connect Hadley Cell to the instability. We should know the what variables can represent a Hadley Cell. Previous studies usually use a zonal mean stream function defined by this equation that's related to the zonal mean meridian winds to define the Hadley Cell intensity. So the Hadley Cell intensity on the northern hemisphere and the southern hemisphere are defined by the maximum value and the minimum value of a stream function at 500 hectopascal. So we think the instability should be related to the stream function. How to do that? I will simply describe these processes. If you are curious about the processes, we can discuss later. If you consider weak temperature gradient balance, we can relate this instability to the vertical velocity gradients. And then when we consider mass continuity and the relation between the meridian wind and the stream function, we can relate the instability to the stream function. So the wave variance has a good correlation with the instability. We also need to see the wave variance should correlate with the Hadley Cell intensity, the stream function. The results show you that the black line is a Hadley Cell intensity compared with the instability and the moisture variance. Northern hemisphere, southern hemisphere below. X-axis is December to November. So you can see that during the boreal summer, there are stronger instability, but weaker Hadley Cell. The Hadley Cell intensity shows a good anti-lag correlation coefficient with the instability when Hadley Cell intensity beats the instability at 1 month. We also can see a good anti-correlation coefficient on the northern hemisphere. So the answer is yes, we see that there are a good correlation coefficient. But why? We should look at the figures. The shading is a 500 hectopascal stream function. We use these variables to define Hadley Cell intensity. Y-axis, latitude, x-axis, the December to November. You can see that during the summertime, boreal summer or austral summer, the Hadley Cell is weaker and narrow compared to a winter season. And it will induce a stronger instability when we consider the 500 hectopascal stream function to calculate instability. And you can think of that because the upward motion is close to a downward motion. They also represent the low-level converging and the diverging close to each other. So that will induce a stronger meridianal gradients. That's why we can see an instability associated with the three variables. They all can show the good correlation coefficient with the black contour, the moisture variance. Therefore, we think a T-type waves can be considered to be a result of the unstable, weaker Hadley Cell. In the summer cell, it's a narrow, weaker, and unstable. It will induce a stronger instability gradients. So the motion mode wave can extract the least energy squared from the MVI, then induce the AD moisture fluxes and the high moisture variability. Based on these ideas, we think if the global climate model has a high instability, that is produce a stronger TD-type waves, we consider 39 CME6 models just focus on the historic scenario. We also use the ERA5 real data as a reference. We focus on the period and the variable average over 10 to 30 latitude north during the July to September because there are the stronger wave variance, AD moisture fluxes, and the instability. The results show you that the left-hand side, the x-axis is moisture variance, right-hand side is AD moisture fluxes. Compared to the meridianal, compared to the instability associated with the precipitation gradients. So the answer is yes. When we can see the global climate model has a high instability, it also produces stronger T-type waves. So there are my conclusions. What determines the T-type waves variability? The FQ, the instability, because that can determine the growth rate of the multiple waves. And why the wave variability is stronger in the northern hemisphere compared to the southern hemisphere. We observe stronger instability in the northern hemisphere. So based on the motion mode and the MVI theory, the northern hemisphere is more unstable to TT-type variability. And how to connect the wave variability to a Hadley cell? When Hadley cell is at its most weaker and narrow, less unstable, the instability reach is maximum. So T-type waves can become stronger. And there are some references. If you're curious about why the T-type waves is multiple, you can check the Maida and Corraliza paper. If you want to see more detail about the equations, how to discuss the interaction between motion mode and Hadley cell, you can check the Maida. Adam's Corraliza and Maida's paper. If you don't want to read the paper, it's okay. They gave the presentation last year. You can check the department seminar on YouTube channel to review it again. So we are very happy. Thanks for your attention. We're happy to discuss this topic and happy to take any questions. Thank you.
Student questions?
Yeah, so you define the strength of the Hadley cell seasonally, and you showed that the instability in the Hadley cell were anti-correlated very strongly. And I think you did this a little bit with your model comparison, but I'm wondering, like, the way that you're defining it, can you define a stronger or weaker Hadley cell within a certain season? And can you see whether or not that holds true for like an anomalously strong or weak Hadley cell within a certain season?
We did that, right? Yeah, we did that. And if you just focus on the summer season, but this should be discussed for other processes. Sorry. Yeah, you mean that if we just focus on the one season, and we have one word, but
I can, yeah.
you want to answer?
Yeah, you can like look.
Because these processes have further processes to discuss, then look at here. Actually, there are other processes after this one. Because when there are stronger wave activities, AD moisture fluxes will transport moisture to a extratropical region. So actually, we are fluxing the what called Lamerian moisture gradient. So when we first focus on the daily data, separate to the weak gradient and stronger gradients, we can see that's related to a Hadley cell. We also see the result. Yes, but when there are the stronger wave activities, it should be weaker than these gradients and also weaker Hadley cell circulation.
That's within like daily.
Yeah, daily.
Scales.
Yes.
Have you done? I mean, you're still looking at like the large scale slowly evolving, like just within a given season. If you like year to year, you could have a summer with an anomalously strong Hadley cell or anomalously weak Hadley cell, and does that correlation hold true like within that?
Yeah, so we submitted a paper like in October that looked at different seasons.
Okay.
And essentially what we did is that we just we just diagnosed how it would all look just based on the moisture gradient. So we assumed that if the gradient is strong, the circulation is strong, and the eddy activity will be weak, and vice versa. And then we just averaged based on an index that's comprised of that's subtropical minus equatorial. And we focus only on summer, boreal summer, because that's where the signal is strongest, and we define the result. It holds on to seasonal remarkably well. And so and the argument that we have is that the energetic constraint to export MSE to the higher latitude, it must be true regardless of how it's being done. So if your cell is weaker, the eddies have to be stronger because the requirement to export energy has to be the same at these longer seasonal time scales. So it works itself out quite nicely.
Okay.
It doesn't hold, so what Qiao-Jun was trying to say, like for example, if you do winter instead of summer, It actually is a little bit more complicated because the extratropical waves in the winter are stronger. So you get more intrusions from higher latitudes, and those can actually do the same thing
Yeah.
that the tropical eddies would do. And so there the results are a little bit murkier and difficult to interpret. But if you focus on the summer, where the Hadley Cell's weaker and the easterly waves and all the TD waves are really strong, then the result comes out really clearly in that season.
Do you think there's...
Was there scatter plots that showed that? In the talk?
Not in this talk.
Oh, not in this talk?
Yeah, not in this talk, but like I have a manuscript I submitted on this. We have the plots for that.
Mm-hmm. Okay.
A follow-up question that is, given the interference from the mid-latitudes, do you think that's part of the reason that you don't see as strong of a correlation in the southern hemisphere? Do you think there's just more interference coming from the southern hemisphere, or do you have other theories for why that's the case?
You want me to answer, or do you?
You mean this part, the southern hemisphere?
Yeah. For all your plots, you showed that you had lower correlations.
TD type was one of the multimodal waves. So there are some other multimodal waves also create a similar role, and we have some result, and yeah, but not in this topic.
So what we think, and this is stuff that she just showed to me a couple weeks ago, is that, so we thought that this would just be better in the northern hemisphere because the ITCC is located in the northern hemisphere, and that all the tropical depression waves are there. But it turns out that you get a really strong signal in the southern hemisphere for equatorial Rossby waves and the MJO.
Okay.
And so it just, what we think, and that's what Qiao-Jun is working on now, and I don't want to like overstep, but like,
It's okay. Really, continue.
is that it depends on the symmetry of the precipitation. So in the northern hemisphere, you have mostly tropical depression waves, and they come really clearly because they're mostly like a localized feature of the ITCC. But equatorial Rossby waves and the MJO, they're more equatorially symmetric, so they prefer a mean state that's more symmetric with respect to the equator. So those southern hemisphere signals come out really strongly in the warm pool where that symmetry holds up. So if you look at the equatorially symmetric waves, you know, which are the equatorial Rossby and the MJO, the signal in the southern hemisphere is just as robust as the northern hemisphere one.
Okay.
So just variability preference in the two hemispheres.
So you can think of that as symmetric and symmetric and anti-symmetric structure based on shape. So there's more symmetric and there's anti-symmetric. There's a maximum in the northern hemisphere.
Yeah, so you can see that in November, so December through March, it's actually like more symmetric. Like it's roughly, approximately, it's not that the southern hemisphere has a southern ITCC, right? It's just that convection is pretty close to the equator.
Yeah.
Yeah. So I think that that's a consequence of the ITCC almost always being north of the equator. So the more you move to the equator in winter, in boreal winter, it becomes more like an equatorially symmetric feature rather than like an off-equatorial feature. So like I think that seasonality causes the different ways to be preferred over different seasons. But they remarkably show the same result. Yeah.
Thank you.
Sorry, you can. Any other student questions?
I guess I was wondering a little bit about, when we talked about in the beginning, a bit about the sort of gravity wave stuff. So I know, I guess you had mentioned that even for shallow clouds, that you still observe that gravity wave or significant in that process. I mean, is there a difference? I mean, I know that for deep convection, you often will have these clouds go up into the tropopods and then extend into the stratosphere and create gravity waves that way. Is there a difference between what we see? I guess the difference in impact between those deep sort of convection gravity waves and the waves caused by these more shallow.
Yeah, so the shallow gravity waves are slower. So the way you think about it is that the phase speed of gravity waves is actually like the product effectively of like equivalent depth. So the larger that depth, the faster the waves propagate. So like what we call the deep convective mode, those gravity waves propagate like roughly 50 meters per second. But the shallower that effective depth becomes, the slower the waves are. So then the waves that are corresponding to shallower clouds, those would be like 10 meters per second. And that's because essentially the shallower the depth, the slower the waves move. Yeah. Does that answer your question?
Yeah, and I guess does that have, when you talk about then the impacts, and then I guess what you sort of like you're saying is this then has impacts on, the development of other, convection in the area, and so then we observe a difference in, like, I guess maybe you can talk about tropical storm or something like NCS, as you see, I guess, development differences then between types of emotive clouds, or does one sort of, do the shallow then become the deep, I guess at some point?
So you're asking a good question there, because that's essentially like, I mean, that's been studied for a long time, right? But you can, for example, this is related to, for example, like Brian May's gregarious convection paper. So you can have, for example, like an active area of rainfall, and then the deep one is actually like warmer. And so like that warming actually would like warm the layer and potentially dissipate clouds, because it's like downward in compression movement. So you would like see like a clearing. But the stratiform one, which is related to the anvil, that has like evaporative cooling, and that would actually induce like a gravity wave that's upward. So you can actually see clouds forming in the wake of those. So like, so the idea back then was that you would actually see active regions of convection clustering around, because these gravity waves are kind of like rippling around, and then the upward ones are actually kind of like bringing air upward. And so yes, that would actually change the morphology. So this it's not just like this one and this one, right? They're just constantly co-evolving and shifting into one another. And I didn't show it here because I didn't want to show too many equations. But under this quasi-equilibrium constraint, if you have adiabatic motion from gravity waves, under this constraint of quasi-equilibrium, you have to have an almost instantaneous response by the clouds in order to maintain the buoyancy the same, because any form of adiabatic motion will cool or warm the layer. So there has to be a cloud response to that change in order to maintain the buoyancy roughly equal to 0. So yeah, so you're right, yeah. In more complicated ways, but yes. Does that make sense?
Yeah.
Cool. All right, opening up for everybody. Questions from broad audience.
Can you go over what your FQ was again?
Okay.
Here, I missed the equations went by kind of fast.
Oh, FQ?
FQ, yes. That's FQ. Okay. And S is the static stability. The big S is the static stability. Yeah. Okay. Okay. And you're calling it FQ because you're thinking of it as like a forcing on the humidity.
For the growth rate of the motion mode.
Okay. So force, like the F is for like forcing, Q is moisture mode. Like that's why you're calling it FQ. Just that'll help me remember it.
Yeah. Yeah, pretty much, yeah. So like forcing the moisture variance.
Okay.
I'm just interested, like, how important the role of F is in this. It kind of goes back to Evan's dialogue about the northern and southern hemispheres. So if you change the region where you have the strong moisture gradient, is F varying enough within 20 to 5 degrees north to have a
It is important.
significant?
Yeah. It's I would say it's about equally important as the gradient, because you don't want F to be too small, otherwise your instability is too small. So it has to be, so that's why you can't get right at the equator. You got very, very little instability. But and that's why also if you look at the plots in Qiao-Jun, you can show the plots. You actually have more instability on the poleward side of the ITCC than the equatorward side, because their F is changing very rapidly. Yeah, so here you see, in these plots, you see that blue. So like the ITCC, so the gradient, you can think about the ITCC being like in that in-between spot. Yeah,
Okay.
yeah. So that, yes, F does matter. Because the precipitation gradient is presumably similar on both sides of the ITCC, right? So the difference is that the north side has a bigger F, so a bigger
Right.
Coriolis than the southern one.
Sure.
So then waves are preferentially occurring on the poleward side of the ITCC. Right. That's satisfactory?
Yeah, I guess so. I guess is there an interplay there? Like the strength of the ITCZ obviously helps dictate the strength of the moisture gradient, but at the same time, that the instability criteria F sub Q also depends on F. So there's perhaps a double interplay there where you move the ITC further north, and the eddies can then get stronger.
Yeah.
Not just because of the presence of the moisture gradient, but also at.
Yeah, because that's also partially why it's so strong in the summer, because that's when the ITCC is furthest from the equator. So yeah, like I said, yeah, F is roughly as important as the
And
gradient.
and
as
the
rainfall gradient.
dynamical interplay there is the role of the Coriolis torque in importing moisture to the TD-like wave.
Yeah, so what's going on is that as the wave develops, so you can think about like, you can, so you're very PV minded, right? So you have a PV gradient, right? And you form a circulation. On one side of the circulation, you're bringing low PV air, and then on the other one, you're bringing high PV air out, right? So you're advecting PV on both sides of the Rossby low. So you can imagine the precipitation gradient. So essentially, you can imagine that rainfall divided by the static stability to be like a PV, essentially, or the moisture gradient. So we just mentioned earlier that the moisture is like a PV, right? In my part of the talk. So it really is behaving like a PV in the ITCC region, where like you're bringing in like essentially low PV and high PV air, but instead of being like actual PV, it's moisture.
Sure.
And that torque that you're bringing in is actually effectively works exactly the same as a vorticity source in sync. So that's actually going to cause the formation of more anomalous negative and positive vorticity on either side of the wave. So the resultant TD type waves behave, so the moisture modes in our theory paper, so I'm taking this because this is related to my paper with Victor. So the way that you can think about it, the moisture modes are almost exactly like Rossby waves in their behavior, but that their mechanism is essentially dictated by the moisture gradient instead of like a PV gradient. But essentially the instability is coming from the fact that your rainfall is co-located with the moisture. So any displacement of that rainfall, and you're moving it to a location where the planetary vorticity is different. So then the vortex stretching from that rainfall / moisture is actually going to generate vorticity through that mechanism. But it behaves exactly like the end result is exactly the same as a PV gradient would behave. It's just all moisture. Does that make sense? It makes sense, perfect sense in my head, but I know that it can
Great.
yeah. So this goes back all the way back to like 2001, like at Sobel et al. That first WTG paper. They talk about this in that original WTG paper. So it goes back, but like I think what that means for the circulation has been slowly fleshed out through the decades, I guess. Does that make?
Yeah, it seems like kind of going back again to Evan's question of like it's the seasonal variability. If you have like a Rossby wave packet or a moisture wave packet, like you showed in the beginning, that 3 of them coming off Africa at the same time. If those are in an active stage of development, then they must be importing moisture. That's the development mechanism for TD-like waves. So there should be a relationship between the interplay, Hadley Cell, TD-like waves, and the development of the packet.
Yes.
And I bet that would be intriguing on
Yeah.
like an S2S prediction. Sort of
So my suspicion, and this is what I the paper that I didn't discuss this here. My suspicion is that the breakdown of the intertropical convergence zone may be related to this mechanism. So we see seasonally that the ITCC sometimes breaks down.
Sure.
And so what I think is that sometimes you get these development of these packets, and then these packets, like the moisture of these TD waves is coming from somewhere, right? Because and back then we didn't have like this quasi-equilibrium stuff figured out. But now with that in mind, you know that moisture is actually not changing that much in space because it has to maintain equilibrium. So then that moisture that the TD waves are coming, it has to be coming from somewhere. So it's coming from the ITCC. So essentially they're robbing the moisture of the ITCC for themselves. So you're increasing moisture variance, which is essentially like the deviations from the zonal mean, by removing the moisture that corresponds to the zonal mean.
Cool. Thanks.
All right, question for, yeah.
Either one of you can take, because my brain is too simple to ask you a useful question here. I was just kind of curious when you describe, I love this interplay between like diffusion and convection, and just like this really tight little gradient. What do you actually mean by diffusion? I don't think you mean molecular diffusion, right? Like, is this really turbulent transport? What generates that turbulence?
Right, it is turbulent transport. So essentially what the first part, like we're assuming, is that you have like that turbulence. So you're essentially thinking, the idea is that you're thinking that the cloud cluster is the scale, in which you have that pressure gradient force. So the scale that you're thinking about is actually the scale of the gravity wave, which is Maxwell scale. So everything that's much smaller scale in that gravity wave is like is the turbulence.
Got it.
So we're essentially just thinking of all that whirling
Uh-huh.
in the convection to be the diffusion. So it's turbulent diffusion,
Got it.
essentially from
Because
the
you
clouds.
mentioned something about one factor being the number of clouds, or the distance between clouds, right? And
Mhm.
so I was just kind of curious, does it matter what a distance between a cloud, or kind of the perimeter of a cloud, right? Like, when you're thinking of like cloud dryer as kind of a driver of that pattern.
Right.
Yeah.
Yeah, so that separation is actually pretty, what we find that is pretty important. So like the time scale in which you equilibrate, it depends on that interspace separation, but also like, I didn't want to like go into a lot of detail, but like that also depends, like the speed in which that adjusts also depends on like how well clustered the clouds are.
Yeah.
So the more well clustered they are, they actually, the process is occurring slightly more slowly. So if you have like a lot of separated clouds, they all will force the gravity waves, and they will all like force adiabatic compression. And so once they overlap, they kind of like already fully adjusted. So it does depend on the width of the cloud elements and the width of the surrounding environment. So it's a little bit more complicated than what I played out, but yes.
Fractal geometry question.
Yeah, pretty much, yeah. So we're trying to like oversimplify this quite a bit, but yeah. So it's essentially what you're thinking, the big idea here is that the individual clouds are like turbulent elements, but that at a larger scale, when you put them together into little clusters, which they tend to do that, so they tend to cluster around, that larger has like an emergent behavior that's dictated by the ways that they're forcing. Even though the little things in them are turbulent. Yeah, and that's maybe a bit of a controversial idea, so don't take it as a fact, right? Like, because clearly not everybody agrees on that. But the big idea is that like things the clouds can be really, really turbulent, but that at the macro scale, all these waves are actually like giving them organization, or helping them giving them organization.
Cool.
One last question, or no? We're out of time. Sorry, we're way past. Sorry. Thank you all.